Machine learning extracts intelligence from raw data. We process datasets through a mathematical algorithm to produce a trained model capable of making predictions. Supervised learning relies on this structured, labeled format. We map known inputs, the features, to a specific known output, the label. However, unsupervised algorithms operate without these labels. Instead of aiming for a predefined output, the system identifies patterns and groups the data into inherent clusters based on mathematical similarity. For this foundation, we will focus exclusively on supervised learning using structured tabular data. While the dataset provides the historical map, the algorithm requires a mathematical engine to learn the relationship between these inputs and outputs. Regression is a subset of supervised learning designed to predict a continuous number, like a house price, or a risk score, rather than a discrete category, like a cat or a dog. Drawing a line of best fit through a simple two-dimensional scatter plot is an intuitive task for a human. You can visualize the trend and place the line by sight. Real-world datasets often involve dozens or hundreds of input features. Factors like location, age, square footage, and local interest rates create a multi-dimensional space where human visualization fails. The challenge for the algorithm is to mathematically compute the optimal multi-dimensional fit through raw data without being given hard-coded rules. Determining that precise line requires treating the data as an optimization problem solved through iterative mathematical refinement. We begin with the standard line equation, y equals mx plus b. The slope m becomes theta 1, the feature weight, determining an input's importance. The y-intercept b becomes theta 0, the bias, providing the baseline prediction before features are weighed. To model complex scenarios, we add more input variables to the equation. By adding theta 2x2 and theta 3x3, our simple two-dimensional line transforms into a three-dimensional plane that can account for multiple variables simultaneously. An algorithm learns by iteratively adjusting these weights and biases until the equation accurately reflects the patterns in the data. The algorithm guesses by drawing an inaccurate line across the dataset. It measures the vertical distance between the actual data points and this line. Squaring this distance for every point prevents positive and negative errors from canceling out, capturing the true total error. The system averages the area of these squares to find the mean squared error. This represents the total cost of the current weights and biases. The mathematical goal of the entire training phase is to minimize this cost function. We use an optimization algorithm called gradient descent to navigate toward the lowest possible error. Think of the error landscape as a U-shaped curve. We start high and must descend to minimize error. The algorithm calculates the slope, taking discrete steps controlled by the learning rate, or alpha. Too small means slow microsteps. Too large causes massive overshooting. Tuning these specific hyperparameters is exactly how machine learning engineers manage the speed and stability of the model's convergence toward ultimate predictive accuracy. Modern Python libraries like scikit-learn compress this entire iterative calculus loop into a single abstracted line of code. Engineers must understand the math beneath the code, because the primary engineering work involves the logic of the weights rather than the syntax of the function call. In practice, roughly half of the workload is dedicated to data cleaning and feature engineering to ensure the algorithm has a viable map to follow. Engineers spend the majority of their remaining time diagnosing why a model failed to converge and adjusting the hyperparameter constraints until the math stabilizes. Structuring the historical data and configuring the optimization constraints to guide the math is the core challenge of the field. The machine learning lifecycle is split into two phases. The training phase uses gradient descent to find the optimal weights, while the inference phase applies those finalized weights to predict outcomes for new, unseen data. Bias is a problem that occurs during the training phase. If the weights are calculated using a non-diverse dataset, the model produces skewed results because it has only learned one narrow pattern of features. High variance is a failure of the inference phase. This happens when a model is overtrained on the training data, making it so sensitive to specific noise that it cannot generalize to the real world. Grasping the underlying mechanics, from cost functions to gradient descent, provides the diagnostic framework required to build and scale reliable predictive systems.